Okay, good afternoon, everybody. Welcome. My name is Thomas Telkamp. As you can see, this is already the third version of the traffic matrices tutorial. Last one was actually at the NANOG in Los Angeles. And I'm always interested to hear feedback from people if there are more topics to add or things you think are incorrect or changes you want to make. Just let me know. Several people have done based on the last version. I incorporate these changes into the slides and use them for next time. So first, a little background on why I'm actually giving this tutorial. For my daily work, I help operators, ISPs or mobile phone operators in modeling and simulating their network. And when I come somewhere, it's always relatively easy to get a topology of the network. You have the router configs to parse and show ISS database output or something like that. But it always proves to be very hard to get traffic data for the network. Where's the traffic going from a router in my network to another router in the network? When I was going over the slides again, I thought it's strange that I can write 90 slides about how to get your traffic data, and still everywhere where I come, it proves to be a problem. So that's the reason I think it's relevant to share this information with you. This is from experiences we have had with several types of networks, several types of equipment, and the things we've learned in doing this. So to give an overview of what I will be talking about this afternoon, first a few general properties of traffic matrices, and these might seem a little bit boring, but I need them later on in the tutorial. Then a section about measurements in IP networks. So in networks where there is no MPLS, how can we know where the traffic is going? The second part about MPLS networks, which give you a lot of extra information about traffic data. Then something about estimation. There have been talks about this topic before at NANOG, and it's something we use a lot ourselves as well. So how can I actually estimate what the traffic matrix is? And then two short topics about how to deal with partial topologies and a few notes about multicast. I have a few acknowledgements to make for people who have contributed to the slides here of whose materials I've used, especially Stefan Schnitter from Deutsche Telekom. The first time we gave this tutorial, we actually did it together. So a lot of the slides in here are made by Stefan. First, a simple definition matter to make sure we're all talking about the same thing. So a traffic matrix represents the amount of traffic transmitted between pairs of nodes in the network. I will often refer to them as demands. So a demand in this case is a entry in the traffic matrix, so the traffic between two routers. The traffic matrix itself can represent either the traffic at a specific time or already some kind of aggregated data, for example, the average over a day or the peak during a day. We see two types of traffic matrices, basically router to router or pop to pop, where with pop to pop you only look at the traffic between two locations, not specifically to which router it's going. I won't be talking very much about that, so we will look at router to router traffic matrices. So also we need to talk about why do we actually need them? Because I can very easily look at the traffic on my network with tools like MRTG, and I see immediately how much traffic I have on every link in the network, and I can see if there is congestion or not. So why would I actually need a traffic matrix for my network? The reason is if there are changes. So the monitoring of the network tells you exactly if everything is fine at that moment in that topology, but you might need to do some capacity planning and say, okay, what happens if I add a link between two routers or two locations where that is not a link yet? I cannot look at the existing link traffic and say, well, it will now be distributed over a new link. I need to know which end-to-end flows will actually run over the new link. Or what if scenarios if I change the topology. Or look at the resilience analysis. So what happens if a router fails in my network? Then I need to look at the new routing, but also I need to know the end-to-end traffic in the network. The last reason is for optimization purposes. Either I want to tune my OSPF or ISAS metrics, Or I want to do something with MPLS traffic engineering. For example, not deploy a full mesh of tunnels, but I just want to only deploy a handful of tunnels for the largest flows I have in my network. So all kinds of reasons why we need to know more than just the link loads in the network. During the talk, I will distinguish between two main types of traffic matrices. First is the internal traffic matrix. So you look at your own network and you figure out where does the traffic come into my network and where does it go out of the network. So it's an ingress to egress traffic matrix. But for a more detailed analysis, also for your external traffic and your BGP routing, you might actually want to look one step deeper into where the traffic is going, and you want to include your neighbors into the flows. So then we have what we call POP, or router to external AS. So I have a router in my network, for example an access router. How much traffic is there to all of my direct peers or transits or customers, anybody talking BGP to you? This can be very useful, for example, to see what is the impact of failures on the BGP links, or what is the impact of changes inside my network on where the traffic will leave the network to my neighbors. I actually did a presentation on what you can do with that data at the RIPE a while back, and there's a reference at the end of the slides where you can find the URL. I'm specifically not looking at the full AS path at this point. So an analysis of where traffic is going multiple hops beyond my own network is a completely different game and completely different analysis from your internal traffic matrix. So a visualization of what I just discussed. In the first case, you have the traffic from an example POP here with 2 core routers to all the other core routers in the network, while if you look at the external traffic matrix, you actually have traffic from core routers to all your neighbor AS. So basically the next hop AS of your neighbors. I want to say a few things about a presentation which was a few NANOGs ago by Van Jacobsen, Hauber Yu, and Bruce Ma about, I think it was called route fusion, where a route flow fusion, it was called, where they made a case for actually not just looking at the traffic, but combining the traffic data, so the traffic matrix, together with routing information. A lot of things they talk about are also covered in this tutorial, but it definitely makes sense to have another look at their slides, because they bring up a lot of very good ideas and approaches in looking a little bit further out of your own network. Also, they make an observation, which we will also see in this tutorial a few times, that is, traffic can possibly go to a lot of places in your own network or further down in the internet. But in reality, traffic actually goes to only very few places. So if you, instead of trying to cover 100% of your traffic, try to cover 95 or 98% of your traffic, your whole problem becomes much smaller, because the number of destinations where it's going is really not that large as the full set of possible destinations. So what they suggest in their paper is, if you look, for example, at net flow data, make sure you also take the BGP routing table into account. Look at the next AS, maybe a few ASs down, record that information together with the flow data. Later on, there is an example on how you can do such a thing with a passive BGP session. Then something about traffic matrices in general, just the properties of the traffic. This comes from an analysis we've done on a tier 1 network. It's actually published in a paper. And it's a network where we can actually measure the traffic matrix, because there's a full mesh of MPLS tunnels. We have 24 hours of data, and we just have a quick look at how the traffic is distributed over time, so what happens during a day, how the traffic is distributed over the network, and how the distribution of traffic is taking place. So first, the temporal distribution, what happens over a day. This is a graph I think everybody is very familiar with from the networks I have seen. If you have a lot of aggregated traffic from your customers, you basically see a very nice daily cycle with a minimum somewhere in the night and a peak somewhere, I think, noon, late afternoon, early evening. It also proves that the peak actually is not a very small moment. It kind of spreads over at least an hour, again, in most of the networks we have seen. So to do any useful work with the traffic matrix, like capacity planning or other planning on your network, it actually proves to work very well to just take a snapshot over an hour or so at the peak of all your traffic. Then we look at the spatial distribution of the network. So if we look at all the possible routers in the network, in this case all the POPs in the network, is there an equal amount of traffic between them, or is it actually focused on just a few places? Well, what you see here is clearly the latter. You have on one side the source, on the other side the destination. The color indicates how much traffic there is between these pairs, where red and yellow are the highest traffic values. We've done that both for a European network and an American network, and they show a very similar thing, that is, most traffic actually is between a few locations. So these are probably your big peering locations, your big customer locations, but it's not like traffic is going anywhere. And this is a theme which comes back several times. With just covering a certain percentage of your traffic, you actually have a very good picture of what's happening in your network. Because if you look at all the blue here, there's really not a lot of very interesting detail in there. Then the last one is a little bit more complicated, but also interesting to look at. That is, if we look at purely the traffic, you get this daily cycle, which I've just shown. But the question is, if I do not look at the absolute amount of traffic, but just at the distribution of traffic. So if I have a router, it sends 100 megabytes of traffic into the network. I'm not interested in the 100 megabits, I'm interested in how many % of the total traffic this is. So a router which is sending most of the traffic in the network at midnight, is it also the router which is sending most of the traffic in the network at peak time? And on the left graph, you see for the largest 4 sources in the network, the total amount of traffic, the very well-known graphs. On the right, you see something which we call the fan out, which is the relative amount of traffic it sends into the network. And during the daily cycle, that number seems to be fairly stable. So a router which is, let's say, large in the evening is also the large router in the morning. This can be a very useful thing to make use of in planning purposes. So then we come to the collection of the data itself. Based on just practical guidelines, I think most networks run queries to the network in around 5 or 15 minutes. If you do less than 5 minutes, you might get into performance issues with the amount of SNMP requests you need to send to the routers, the amount of data you need to store. If you take longer intervals than 15 minutes, you actually start losing granularity, because there might happen interesting things within a 15-minute interval. What you measure for all the different methods I will be showing later are the byte counters. So most of the time you don't get a rate, but you get the amount of traffic which has been sent over an interface or sent into a certain accounting bucket. So you do this multiple times, you subtract the traffic, and based on the interval you can actually calculate the rate. I already said a few things about what kind of traffic matrix you can generate from that, so either a peak or an average over an hour. And in a lot of cases we've seen just taking an hour at the time you know the network is going to peak works perfectly well for planning purposes. So then we come finally to the collection of the traffic matrix itself. For IP networks, the 4 major techniques I'm going to talk about are NetFlow, then BGP policy accounting and DCU, which are kind of the same thing on the Cisco side and the Juniper side. Then the estimation. MPLS actually, of course, doesn't apply to the IP networks. So NetFlow, I think everybody knows in some way, because it's used a lot and mentioned everywhere. I think there's even another tutorial on NetFlow in the afternoon for security aspects. And I'm not going to cover NetFlow into an extreme detail, also because it's such a wide area. There's a lot of different flavors of. First, again, the definition matter. A flow in NetFlow terminology is defined by all the IP packets that have a common source, a common destination, a source port, a destination port, protocol type of service, and the input interface. So even traffic between two hosts on the network or on the internet may generate multiple flows. So clearly, it tells you a lot of detailed information, which can be extremely useful for things like security or denial of service attacks, etc. But for just getting a traffic matrix, we really don't need this kind of detail. The router keeps track of these flows, and for every entry it has created, so for every new flow it sees, it will keep a counter for the bytes and the packets. There are a lot of versions out there for generating NetFlow records. The most common one and the most widely deployed is version 5, which is basically exactly what I showed on the previous slide. The flow records are exported in a very raw format to a collector, and I will show an example later. Then there was version 7, which is specifically to switches. Version 8 and 9 are the newer ones and actually the more interesting ones, because there you can aggregate data on the routers. Instead of sending all the data to a host somewhere far away and then trying to do some correlation, you can actually already filter out all the useless information on the router itself. The nice thing about NetFlow is that it's fairly widely deployed on Cisco, Juniper, and various other router vendors. So the thing is, we need to get the flow records from the flow cache on the router to some kind of collector. The router decides on when to export the flow, either when it expires, so in the case of TCP, when the session is closed, or in the case of UDP, when a timer expires, or when there's simply no room anymore on the router to store more information, then it will export things, or when it just times out for any other reason. It will use UDP to send it to a collector, which is unreliable, so if traffic is lost between the router and the collector, then it will not be recovered or retried or anything. This is a good thing, because if something goes wrong, you don't want to back up megabytes of flow records somewhere on the router to retry later on. So the way this works, in a picture from Cisco actually, you have the NetFlow cache on the router. At some point, because of one of these reasons, the flow expires and you send it to a collector, which generally is some kind of Unix machine collecting these flow records. Because the amount of data can be fairly large, I think in the packet design presentation they mentioned something like 1% of the link bandwidth you're measuring, you're enabling NetFlow on, is actually required to send the NetFlow records to a collector. And that's quite a bit of data if you look at gigabit or 10 gigabit links. And not only to send it over your network, but also to process and store it. So a lot of deployments I've seen for NetFlow collectors have multiple collectors at different locations just to keep things scalable. But the main problem with NetFlow for the purpose of generating a traffic matrix is that you need to convert those flow records to something we can use. As I showed on the first slide, the flow record actually has a source address, a source IP address, and a source destination, and a destination IP address. But that's really not what we're interested in, because in most ISP cases, both the source and the destination, or at least either one of them, is not on your network. So what we want to know is, where did the traffic come into the network, and where did the traffic leave the network? So to start, we enable NetFlow on all the external interfaces on facing outside of our network or from the access router to the core. So at that point, we already know where the traffic came into the network based on the place where the NetFlow record was generated. So I know the incoming interface or the incoming router. Then, if I export it to my collector, I also need to figure out, okay, where is this traffic going into the network? So I need routing data or some kind of information either from a static list. So if traffic is going to a set of customers and you know what their address space is, you could generate a list which says this address goes out of the network at that location. Very inconvenient and not very scalable, of course. So I think most networks will do such with either communities in BGP or looking at the BGP AS. So in the NetFlow record, you can export the AS number where the traffic is going to leave your network, and that will tell you where it's going to have the egress point in your network. So this is not a simple thing to do, and there are commercial products performing this task for you, and often they already do other things with NetFlow like security or DDoS, things like that, and this comes on as an add-on. They can also give you the traffic matrix. So instead of having the router in real time do lookups for every flow on what it should export for the AS, it's a better approach to actually run a BGP passive peer on the collector itself. So there is a BGP session between the collector and one or more routers in the network, and the collector actually has a full BGP table. So the router will just export the raw record, and the collector will do the lookup in the BGP table. This also comes back to the packet design presentation, where they have shown that you can at that moment also use much more information than just the destination AS or the neighbor AS. You can look one step deeper and see next to your, so behind your peers, what are the interesting networks to look at. So they propose the same approach here. So it's better for the routers because the router doesn't have to do the BGP lookup and the AS lookup, and it tells you much more, or can potentially tell you much more on what's going on. There's another very tricky thing to keep in mind when looking at these flow records. If we have here a setup, and in this case we are AS3, and we're exporting flow records from the router there in AS3, and we're looking at traffic from AS1 to AS4. The path based on BGP setup is AS1, AS2, AS3, and then to AS4. So if I export my flow record, it says destination AS is AS4, which is correct. And it says the source AS is AS1, which is also correct because both we know from who is advertising that IP address. But if we at the same time look at how the routing in the reverse direction works, so we have traffic, supposedly traffic from AS4 to AS1, you will see that, and this is just an example where the policy is such that it will actually be AS4, AS3, AS5 to AS1. So there's an asymmetric path. Now if we ask the router to export the peer AS, so to tell you actually which is your neighbor which is sending you the traffic, it will tell you it's AS5, because that is what it sees in this network. It looks up the prefix in AS1 and it sees, well, I'm using AS5 to get there, so it probably also came from AS5. But in the case of asymmetric routing, that definitely is not the case. So just looking at these flow records and then deducting what your neighbor ASs are can be tricky. You really need to look at which router it came into your network. Then the newer versions of NetFlow have big advantages over what I've been just explaining, because they can actually perform aggregation within the router. So instead of exporting every flow record, you can say, in the router itself, sum all the flow records up which have traffic to a certain prefix, or all the flow records which have traffic to a certain AS. That immensely reduces the amount of data you need to send from the router to the flow collectors. So where with version 5 you probably on a large network need multiple collectors, you here could easily do with one, because it's much less performance issue of processing it. On the router itself, there's not a whole lot of difference because it's still using the version 5 cache. It's just an add-on which actually does the aggregation. There are multiple of those aggregation schemes, either per protocol, per AS, per source destination address, etc., whatever you think is relevant. So again, the same picture. The cache, as I said, is still there, but the flow is not exported directly, but it's using an aggregation scheme. These aggregation schemes are exported in a certain format to the flow collector, multiple at a time if you want to, and also at a certain interval. There's also a new aggregation scheme which I've been using myself in a few deployments lately, which is the BGP next hop aggregation. This is really easy because it will tell you for traffic on a certain router, not the destination where it's going, but it will tell you which is the next hop in the BGP table. Normally, that is your egress router on the network, because BGP will have a next hop, which is an IGP address, which is a router somewhere else in your network, where it has received the route towards where your traffic is going. So this brings you very close to directly getting your traffic matrix, because you're at some access router, aggregating customers, you aggregate on BGP next hop, and you exactly know from that router, I have traffic to these BGP next hops, which are your egress routers. The only issue you still have is that it doesn't work for IGP-based traffic. So if your destination is in the IGP, maybe a server farm or something internally in your network, it will actually give all kinds of zeros as a next hop. So here you see where you would enable the net flow on the interface, which is on all your external facing interfaces, and then it will tell you nicely for, well, if you look at the AR on the left, it will tell you which AR on the right the traffic is leaving the network. This you can do with the version 8 inside the router, but some of the flow collectors, and I know the one from Cisco, for example, can also do this on version 5 information. Then there is something called MPLS aware net flow, which gives you some more information than just based on the IP header. In the case of MPLS, like with LDP, you know the facts, so you actually know where the traffic is exiting as well. I think in most cases where you have an MPLS deployment, the BGP next hop will also work and maybe even give you easier results. Because if the MPLS is used for VPNs, the BGP next hop will perfectly work because it's all based on BGP. So I have not myself seen a useful deployment of this feature anywhere yet. So as I said, this is really a high-level overview. If I would go into the details here, it would be a complete separate tutorial. But there is a lot you can do with NetFlow, especially if you already have it running for some kind of other reason, like security analysis. It's not so simple to generate a traffic matrix from it because, well, you need your ingress egress. You have the issues with which is your neighbor AS, so which is your peer AS versus the original AS. And it's fairly CPU intensive on the routers. Of course, you can do sampling to get less processing, but then you have all kinds of issues on how accurate the sampling is. Also, there are so many different types of routers and types of software versions out there that I really don't want to keep track of exactly what's implemented where. There is a very nice webpage from Benoit Claes where he has links to presentations with much more detail about all these different types of NetFlow than I have here. Also, there are multiple commercial tools available which will do all of these things I've shown here. Arbor is, I think, a very well-known one. I've seen Atlex, which can do the setup with the passive BGP connection, for example. In my own experience also, even if you have picked a nice aggregation scheme and have all figured out how to deploy it, you almost always run into some kind of issue because there's one router which doesn't support it, which has a different version or different hardware or different vendor. At least in my experience, it's very hard to get this network-wide running. Next one is BGP policy accounting, which I personally think is a very simple and nice mechanism to get very useful data. What it basically does is you have a certain amount of counters, buckets, where you can count traffic in, and you can assign them to access lists which use BGP. So you can either match it on neighbor ASs or things in the AS path. You can base it on communities, which might be the easiest one. So, for example, on all your peers, you give every peer a specific community number, and then you make in all the routers an access list which says bucket number 1 is peer 1, bucket number 2 is peer 2, and you keep track of which one is which. You run the BGP policy accounting, and for all the traffic towards any of these BGP destinations, it will nicely count how much traffic there is. It's very easy to retrieve this information because it's all in SNMP MIP, and it's fairly simple to extract it from the router. Of course, there's always a limitation, and in this case, it's that there are only 64 buckets. So it's simple, it works good, but you can only count traffic to 64 destinations. This might not be that bad, because here we have another example on where you might not need to count all the traffic. If with 64 buckets you can actually count 90, 95, 98% of your traffic, you might be perfectly fine with the solution. As far as I know, this is a Cisco-specific solution. Then on the Juniper side, there is something fairly similar, or almost exactly the same, which is called destination class usage. I think in the newer versions, it's actually a combination of source class and destination class usage. So it does the same thing based on communities or other properties you can set on either a BGP route or an IGP route. You can count traffic into buckets and do your accounting that way. A nice feature here is that the data is actually stored in a file on the router, which might make retrieval even easier to implement than using SNMP, because you can just make a script which takes the file out at certain times, runs it to some parser to put all of the routers together, and you're done. The older versions of Junos, and I don't know exactly till which version, had support for only 16 buckets, which I think is a little bit too limited to do proper traffic matrix accounting. But as far as I'm aware, the current versions, which probably most people running Juniper have deployed, does 126, which I think is a very good number to do as a total number of accounting buckets in your network. So a simple example here. You have a network with on one router all kind of customers connected, two other routers which have connections to your transit provider. You mark them with a certain community, or you look at the AS, but if you have multiple connections to the same AS, probably communities is better to actually distinguish between the different exit points. And on the interfaces from the customers, you run the DCU, and you nicely get how much traffic goes from that router to either of these transit providers. If you even want more granularity, you can use the combination of source class and destination class, so you can actually also do it per incoming interface, and then you know how much traffic there is from a certain customer to a certain transit provider. Again, with the limitation of 126 sources, 126 destinations. Simon Leine from Switch pointed me to a nice web page he has made with the URL written down here, where he explains a bit on how you can access the data for both BGP policy accounting and the Juniper DCU. He also has provided a library for using SNMP and Perl. There are links to the MIPS there. So if you're ever interested in doing something with these features, that would be a very good place to get started. So till here for the getting statistics from the pure IP networks. Now we'll have a look at MPLS deployments. So in MPLS networks, we actually can distinguish between two types of deployments. You either have an LDP network, where you have labels for transporting, for example, VPN traffic or layer 2 traffic over your network, but your routing just follows the IGP routing as any IP packet would do in the network. The other option is RSVP, traffic engineering, where you have traffic engineered tunnels through the network, with a specific path, either set up dynamically or statically, where traffic which is forced into a tunnel takes a pre-set up path different from the IGP. Both of these solutions give some useful information for traffic statistics. At the end, I have a few comments, so from Stefan Snito's slides, on how they have deployed this within Deutsche Telekom. So the way this looks like in a Cisco router is that you have an interface for the traffic engineer tunnel. So we're looking here at the RSVP traffic engineer tunnels, and a certain path associated with it. Based on where the tunnel starts, traffic is routed into the tunnel, either as part of a VPN or just because of it's integrated in the IGP, and it will follow that tunnel. A lot of deployments for this type of traffic engineering actually have a full mesh of tunnels. So from every router in the network, you set up an MPLS traffic engineer tunnel to every other router in the network. What you get is a mesh of n times, if you have n routers in the network, n times n-1 tunnels in the network. There are lots of scalability issues with this kind of deployments, especially on larger networks, because it scales as n square with the number of routers in your network, and managing tunnels can be very hard to do. I have some experience from a previous job with that. But it also gives you advantages, because all the traffic which goes into such a tunnel is automatically counted as an interface counter. So these tunnels show up as interfaces in your router. Even with MRTG, they will pick them up and automatically show the traffic to all these different destinations. So if you deploy a full mesh of tunnels, you automatically have a full mesh of a full traffic matrix between all the points where you have these tunnels. So on the downside, deploying a full mesh of MPLS TE tunnels is a lot of effort. People need to understand how to troubleshoot it, how to monitor it, and if there is no reason to do traffic engineering, I don't think anybody would even consider doing this just for the traffic statistics. Also, the tunnels don't do any load balancing anymore. So if your network is based on a lot of load balancing, then with tunnels it might get harder to get a proper traffic distribution. So if you run MPLS traffic engineering with full mesh, you have your nice stats. If not, this is not a relevant solution. This one I think is more interesting and also more applicable to deployments. So if LDP is used for label distribution, which for example in all VPN enabled networks will be the case, then traffic coming into a router on a certain label is switched out to an interface using a different label based on the routing which is already set up by the IGP. The nice thing is though that for every packet it switches, for example here a packet with label 1234 coming in, label 1235 going out, there were already 4,000 bytes switched. If a new packet comes in, it will actually update the counter. So for every byte, for every packet switched through LDP to the network, every router keeps a counter on how much traffic there is. So these counters we can use to generate our traffic matrix. The nice thing is, if you have ECMP in your network based on IGP routing, LDP will just do exactly the same thing. So if I have traffic coming in here from router 1 to 2, and 2 is load balancing it, then the one label coming in will actually split in 2 labels going out and follow the same routing as before. And at the final destination, the 2 labels will be merged again into a single stream. So how can we use this to generate the traffic matrix? Because it's not as easy anymore as with tunnels, which have a clear beginning or an start and an end. Here we need to figure out more on where the traffic is coming from. So one of the issues is if we start at a random router in the network and we see traffic over a certain MPLS LDP FAC, how do we know where the traffic came from? Where is the start of that traffic? So if we look at the path through the network, so we have a route starting at A, going to B, via several other routers exiting at Z. Every router in that path will keep a counter for the traffic towards destination Z. So if I have a packet coming from router A to B over the whole path, it will be counted everywhere. If I have a packet which starts at B, it will be counting everywhere except at router A. So the idea here is I look at the traffic on every router in the path. I know where it's going because I know what the FAC is. And I know that the traffic from the previous hop I should subtract because that already has been counted. So if I see 100 megabits towards Z at router B, and I know that there is 50 megabits towards router Z at A, then I know that the remaining 50 must have entered the network at B. This sounds a bit complicated, but it really isn't. And there's a very nice paper about it from Martin Horneffer and Stefan Snitter from Deutsche Telekom. They have implemented it, and they describe exactly the algorithm for processing this on the network. So here's an example on how that would work. As you don't know where to start, we will here show what happens if you start at router 3. You pick a random router in the network, you look at how much traffic there is, and you know that the traffic you see at this hop, I need to subtract from the next hop. So here we have an example where there is 20 units of traffic, let's say 20 megabits, 20 bytes, doesn't matter, from router 1 to router 5. We want to create a traffic matrix, so if we're done, there should be 20 in the column from 1 to 5. So let's see what happens. We actually start at router 3, and at router 3 we see 10 units of traffic because of the load balancing. So the traffic actually at router 2 has split over the two paths. So I know at this point that there is 10 units of traffic from router 3 to router 5. From the information I have at this point, I process the next router, which is router 4, and there I see another 10 units of traffic from router 4 to router 5. So there I put also in the traffic matrix 10 units from router 4 to router 5. Now I look at router 5 itself, which has no information because that's the destination of the traffic. Then I come to router 1. At router 1 I see 20 units of traffic, which were actually coming into the network there. So I put 20 in the column from router 1 to router 5. And I put at the same time minus 20 at the next hop, which is router 2. The reason is I want to subtract the traffic which came into the network at A, at router 1. I want to subtract it at router 2 because I don't want to double count it. So I do that. Then I process router 2, and that there I have 10 units going out. I add them, so I see 20 units in total. I add them to the minus 20, which I had inherited from the previous hop, and it nicely zeroes out. And I have my proper traffic matrix, which is 20 units from 1 to 5. I know this example is not the best possible. And I suggest if you're really interested in this method, have a look at the paper, which shows in much more detail on how this works. Also, there are some practical considerations of doing this. And on one router vendor, it actually is easier than I show it here, and on the other, it's actually more complicated than I show it here. To start with Cisco, on iOS, there is an issue that instead of showing all the LDP traffic towards a certain destination, it only shows the transit traffic. So if I have 50 megabits transiting through my router to a destination, I count that, but if there is another 20 coming in, so it's actually being encapsulated there in MPLS, it's not being counted. So I kind of lack information on where the traffic comes into the network. Traffic only shows up at the next hop, not at the hop where it came into the network. This might or might not be a problem. For example, if you see the small topology I have there at the bottom, if all the encapsulation is done at the access routers, then, and I see the traffic showing up at the core router, in this case the label switch router, LSRA, then I know where the traffic came from. I see traffic showing up, I see my incoming links, and the numbers will match. If I have a mix of encapsulation and transiting on the same routers, then it's going to be very hard to figure out where the traffic came from. Also, the paper has some more detail on what to do in that case. The way this looks on the CLI is that per forwarding entry, in this case an IGP destination, you see an amount of bytes switched. And the thing to keep in mind is these are not all the bytes switched, these are only the bytes which were actually coming in as MPLS and going out as MPLS, not the bytes that came in as IP and go out as MPLS. Obviously, this was the one which was trickier. On Juniper, fortunately, it's a little bit easier to process. The nice thing there is that Juniper actually has different counters for both the transit traffic and the ingress traffic. So it tells you how much traffic came through the router to a certain destination. It tells you how much traffic came into the router from a different source towards the same destination. The only thing Juniper doesn't show is which are the outgoing interfaces. So if there are multiple, then you will have to assume that traffic is load balanced equally, which I think in most core networks with a lot of traffic is not a very unfair assumption. Again, an example on how that looks in the router. You see very nicely to a certain FAC, so a certain destination, you see two counters, one for transit, one for ingress. You see the number of packets and number of bytes. This is really easy to process. All you need to have to figure out is which are the routers in the chain, and you're done. It's actually even easier because you can even also look at just the ingress traffic, and it tells you immediately from this router I have so much traffic to that destination. So the whole algorithm I showed before actually doesn't even apply to the Juniper router. You directly get the statistics. As I said before, this is not just something we made up. This actually has been deployed in Deutsche Telekom on a fairly large network. They run all of this on a single PC. They have a script which logs into the routers, does the show command, parses the outputs, puts it together in the traffic matrix, and they have very up-to-date, very accurate statistics of exactly where the traffic is going. The whole process in their case looks like first figure out what the topology is based on the router configs, then look at the LDP data and do the algorithm as I showed before. Then they have to do some scaling because they have the issue that with the Cisco you only see the ingress, the transit traffic, so they have to figure out some things on where the traffic was coming from. And then they transform it into the proper traffic matrix and they do all the planning, failure analysis with that data. And again, I keep saying it, there's a nice paper about it, there's a reference at the end of the slides, and it's worth reading. So, conclusion, not much news here. It works in a multi-vendor environment, it gives you direct results, it's not a whole lot of processing, and very worth exploring. Then I come to a large part of the tutorial about traffic matrix estimation. This is a fairly new topic. There have been several presentations at NANOG from especially AT&T, I think, on this topic, on how you can do this in your network, how you can do it fast and reliable. And in my experience, when we need to have very quickly some data to get started on, estimation always is the way to go, because you can get your link statistics from the network, and you don't rely on all these different things I've just discussed, which are not that difficult, but they require some work to roll out and to script. So, let me skip this one. What we really want is figure out what the traffic matrix is from something we can directly measure. So we don't have to set up anything, no configuration in the network, just look at the link utilizations and figure out where is my traffic going. So to formulate the problem we're going to look at is, how do I estimate my point-to-point demands from the link utilizations I see in MRTG or any other tool? This idea was first published by Yehudi Vardi in 1996, and mathematical, it's a problem which shows up in different areas as well, like seismology, MRI scans. They have similar problems to solve than we try to solve here. So this is a funny thing I discovered in a paper already from 1937. So we have talks here at NANOG pushing new ideas about traffic matrix estimation, but it actually was written down in 1937 by a Dutch engineer called Kruithof. This was around the time that the Erlang formulas were discovered, and he wrote a kind of angry article, and he says, it's very nice that we have all these formulas to calculate what the blocking chance is on a link, but what purpose is that formula if I don't know how much traffic I have? What am I going to apply it to? So he came up with an algorithm which says, here I have all my telephone switches, I know how much traffic goes in, how much traffic comes out, and he published a very simple algorithm, an iterative algorithm, to estimate what the flows are in the telephone network. This algorithm is, if you generalize it a little bit, directly applicable to what we do on IP networks today. So it's not new, but still a very good idea. So the demand estimation, as it's called, what we try to do is from a set of data we have, which is the link utilizations. If you have n nodes in the network, the number of links will be order n. So maybe it's 2 times, 3 times n, something like that. But what we need to estimate, the traffic matrix, actually is n squared. So we have little information from which we try to estimate a lot of information. So obviously, this cannot be done with absolute certainty. There might be multiple solutions. So what we're actually going to do is we're going to estimate a traffic matrix, which is the most likely traffic matrix. There are many algorithms which can do things like that. A lot of papers about them. There's a gravity model, maximum likelihood estimation, entropy maximization, and I think the point to take away from all these papers is it really doesn't matter too much which algorithm it is, because they basically give all rather similar results. I'm sure lots of people will disagree, but I think it is. So these algorithms work on very large sets of data, and there's no way you can look at the data and understand how it works. So here's a very simple example, which you can just go over the algorithm step by step on how it works. We have a network here with routers in Paris, Brussels, and London. And the only thing we know is that on the link in the middle there are 6 megabits of traffic. Also, we know that there are 2 flows over that link. But we know that from the routing table. So the Paris-Brussels and the Paris-London traffic is there. So the only information we get from the network is the sum of Paris to Brussels and Paris to London is 6 megabits. Nothing else we know. So whatever we come up with a solution, it needs to fit the equation Paris to Brussels plus Paris to London is 6. So if I put that in a graph, and on one axis I put the traffic Paris to Brussels, on the other axis I put the traffic Paris to London, I know that it needs to be on the line, on the thick blue line there. That means if there is no traffic from Paris to Brussels, there must be 6 from Paris to London. And the other way around, or 3 versus 3, or 2 versus 4, any solution on that line. So basically we're kind of stuck, because where would a solution be to this problem? There, we actually are going to generate some extra information. In this case, a gravity model. So we're going to look at the overall network, and we see that in the total network, Brussels is responsible for 2% of the overall traffic. London is responsible for 8% of the overall traffic. So the extra information we get here is that London is 4 times larger than Brussels. So what we could assume here is, say, well, if London is larger than Brussels, then it's most likely that from Paris there's more traffic going to London than there is to Brussels. So if we put that assumption in there, and we know, we estimate it's 1 megabits Paris to Brussels and 4 to London, because of the total traffic, the 50, we bring 2% to London, 2% to Brussels, 8 to London. We see that, although it's an estimate, it doesn't fit the solution. So we have an estimate, we have a requirement for the solution, and the only step which is required is how do we get from our estimate towards a point which is part of the solution. So all these different algorithms actually just figure out how I find the shortest path from the red dot to the blue dot on the line. And so the blue dot can move a little bit, but it doesn't matter too much on exactly where it is. It needs to be in the right area. So in this very simple example, the best guess we can make is that Paris to Brussels is 1.5 megabits, Paris to London is 4.5 megabits. If it's true, we don't know, because this is the information we have. We could enable NetFlow to see if it's true, but this is the best guess we can make. Obviously, this was extremely simple, but you can imagine that you can do this with 1,000 links and 500 routers exactly the same way as I just described it here. What you actually do is you formulate it in a more formal way, where you make a routing matrix which tells you which demand runs on which link, and you get equations like the ones I've shown before. So more relevant for us here right now is how well does this work on my own network. The nice thing is we have been working with several networks, so we actually know what the traffic matrix is. For example, in the network for my previous employer at Global Crossing, we had this full mesh of tunnels in the network. And so we had an exact traffic matrix. We know where the traffic is going. So it's an ideal case on testing all these different algorithms, because I can look at the link loads, I can run my estimation algorithm and compare it to the traffic I see on the tunnels and see if it matches. So we've done that here in this graph. On the x-axis you see the known demands. So those are the demands we've actually measured on the MPLS tunnels. On the y-axis you see what we've estimated. Now, the first thing you see here is that it's not at all accurate. If it was a perfect match, everything would be on the thick blue line there, but you see that there is a lot of spread around the line. The good news, though, is that the algorithm did pick out the large demand. So if a demand is large in real life, it will also be large in the estimation. It might not be exactly accurate, but it does a fairly good job in getting demands into the right direction. So the first conclusion might be that this is very disappointing and doesn't work at all, and just discard it. But what we need to realize is that we're not so much interested in the demands themselves, because we're not going to use them for billing or something like that. What we're interested in is using them for resilience analysis, for capacity planning, for optimization, anything like that. So the question is, if I use this estimated traffic matrix, which I know is not very accurate, and I use it for failing every link in the network and seeing what happens, will it give me the same results as the real traffic matrix? And then the amazing thing happens. So here we've run a failure simulation for a full network. We fail every link in the network one by one. We look at all the other links, and we keep track of the highest load we see on any of these links. So it's a worst case analysis of every possible failure. This will tell you if there is congestion somewhere in the network based on a possible link failure. We do this using the traffic matrix we've estimated. We do this using the traffic matrix we have from MPLS. And it's amazing, but it just exactly gives you the same results. So for this purpose, the estimated traffic matrix actually did extremely well. So there is an explanation behind this, because it looks a little bit like magic, like you have this total garbage data and then suddenly everything works out perfectly well. But there is a good explanation behind it. We're here trying to estimate individual demands, which there are a lot of them and they are very small compared to the total traffic we see on the network. But if you do a failure analysis or something for capacity planning, if a link fails, traffic is not distributed randomly over the network. So if one of my big links of the ocean fails, there might be 2 or 3 more. So traffic will redistribute over 1 or 2 different paths. So these demands actually stay together in groups. Half of the traffic might go one direction, half of the traffic might go the other direction. I might have trouble estimating these demands individually, but together I can actually estimate them fairly accurately. And that's exactly the effect you see happening here. So for your deployment purposes, it gives you very good data. We can even make it better, and I've now presented it as an either-or solution. So you either do something with DCU or BGP policy accounting or NetFlow, or you do estimation. But why not do both? If you run an estimation, you will figure out where are your large traffic demands. Once you know them, you can set up BGP policy accounting on just a few routers. That will exactly pin down those very large demands, and everything you have left, you can estimate. If you look at the error in the data you have, you see in this graph here that actually after adding just a few measurements, your average error in the data goes down to almost zero. I have to admit this is also a little bit caused by the fact that most traffic is just carried by a few demands. So if you know them, obviously the error in the rest becomes much smaller, but well, it's not fake, it's real. So this was the overview on how it works. We did actually another case study, kind of similar to what I've just shown, on a different network, also one where we have the traffic matrix from LDP, and we've done a similar analysis. So we have a network of about 80 routers, 200 circuits, a traffic matrix of around 2,550 entries. The reason it's not exactly n square is that the core routers don't source or sync traffic, so they're not part of the traffic matrix. We know the traffic matrix because you can measure it, one of the methods I've explained before. And in this case study, we look at a few different evaluations. First of all, how do the two matrices compare? The second one is how well does it predict the worst case link utilization? So if I do a failure, will it tell me exactly what's going to happen? And if I use it for other tools, for example, in a tool for optimizing IGP metrics, there are several papers out there and implementations, will that also give me the same results? So the procedure for this comparison is as follows. We start with a traffic, a network with a known traffic matrix, which we call plan A. We run a simulation, so we know exactly what the link loads are everywhere in the network. That we call plan B, and in plan B, we only have the link loads, so we don't have the real traffic matrix anymore. On plan B, we're going to run an estimation process, and then we're going to do these various evaluations on both plan A, the original plan, the estimated plan, plan B, and compare them to each other. Here you go with estimating the traffic matrix itself. Again, on the x-axis you see the real traffic, on the y-axis the estimated traffic, and a fairly similar result to what I've shown in the first picture. It basically puts the demands in the right direction, but extremely accurate it is not. Then we're going to look at all the failures. So both networks fill every link, keep track of the highest utilization we see on every other link in the network, compare them. And again, here you see a similar thing, that they provide almost exactly the same results on the estimated and the real traffic matrix. And we've done this on actually more than those two networks, and we see it in all those cases happening. Then we go to a little bit more complex case. Here we're going to optimize the network. So we have this tool which you give it a network with traffic and a certain routing, and it's going to find better metrics to better load balance the traffic, or actually get your utilizations down in the network. Basically, get more traffic over the same network by picking different OSPF or IRCS metrics. So what would happen if we feed this inaccurate estimated traffic matrix into that estimation process? What you see here is that on the x-axis again, based on the measured demands, optimize the network, and looking at the link utilization, so the link loads using MRTG or something like that. On the y-axis, based on the estimated demands. Here you see that they don't match at all. So if I give it the real traffic matrix, it comes up with a solution, and for new metrics and therefore new routing and new link utilizations, same for the estimate, but they don't match with each other. That does not necessarily mean that one did worse or better than the other. It means they did something different. So what I'm going to compare in this case is not link A to link A in the other network, but I'm going to compare the highest link in one network to the highest link in the other network, the second highest to the second highest, to see if they give the same type of results. And what happens? They basically give the same results. There's a few differences. The estimated utilization, actually, I think it was something like 5% higher than with the real traffic matrix. But if I compare the link based on an ordering, so the highest to the lowest, it actually gives a comparable good solution to my new, using my new metrics. The thing is, they're different. So it gives you a different solution. Exactly the same analysis for the worst case utilization. So again, optimize the metrics, compare them, but now look at all the failures as well. And again, you see that there is a little bit of difference between the two networks. The difference actually is smaller than before, also because if you take a link out of the network, the remaining number of choices you have is just smaller, so it needs to be closer together. And again, if I order them, you see that they actually give, well, pretty much the same results for these, for the estimated versus the real traffic matrix. Then, the thing I showed before as well, what happens if I add measurement data? So in here, in this case, I estimate my traffic matrix. I take the 100 highest demands from the traffic matrix, from the estimated traffic matrix. Those I measure. I set up DCU or BGP policy accounting on my network to measure exactly those demands. And then I run the estimation again, but now I fill in the demands I already know. And it shows that with just running DCU on 100 of these demands, which covers 38% of the traffic, you get all the large traffic perfectly accurate in your traffic matrix, and all the smaller ones still have some variation. I can take a slightly different approach and say, well, I don't want to go everywhere in my network and configure 1 or 2 buckets. Just take the top 10 routers. On the top 10 routers, you configure either NetFlow, policy accounting, DCU, just on 10 routers. Use that data to improve the estimation and see how that works. And here, on 10 routers, you actually capture 41% of the traffic. So remember, this was a network with, I think, about 80 routers. So on 10 routers, you have actually 40% of the traffic, which shows again that most of the traffic is just at a few places. So the combination of estimation and measuring a few things is, I think, very powerful, especially because it's still kind of scary to fully rely for your planning and failure analysis on just estimated values. If you can measure them, it gives you some confidence on at least my large flows are accurate, and it gives you an idea on how well the estimation did. So you can keep an eye on if things are still in sync. If I run all my simulations again, it even gets better, but it already was doing pretty well, so there's not much news to add there. So to take away from this, I think from all the experience we have with this technology, it works very well. You don't have to just believe myself. I mean, AT&T has been telling the same story here, also backed up with results from their network. And what we see is very much in line with what they have seen. And the combination makes it even better. Another thing AT&T has pointed out a few times in their presentations is you can even do this including your traffic to the peers. So you're not really going to look at the BGP routing or the AS paths, but you just estimate the traffic up to the remote peering router on the other side. In the case of AT&T, I think they even mentioned that it made the solution more accurate, but also, as I explained before, you can use it for simulating failures on the BGP links themselves. So this method is not restricted to just staying on your own IGP topology. So again, the presentations here at NANOG have always been on a kind of research type level, but really it has moved beyond that. The algorithms are not that hard. Some of the papers actually give you some sample code on how to do it. If you really want to, you can do it yourself. There are commercial tools available doing this, and I think it's also in the Totem traffic engineering toolkit from the university in Belgium. I think they have an implementation as well. I didn't have a chance to check it myself, but I read, at least on their website, that they have an implementation in free software available. And it can be used in many different scenarios. Also, for example, where you have a partial MPLS mesh and want to estimate the rest of the traffic. And I highly suggest you take a look at the AT&T work. Again, there's a reference at the end of the slides. Okay, we're also almost at the end. I have two more small topics which are kind of related to what I've been discussing before. First, traffic matrix and partial topologies. There might be all kinds of reasons why you do not want to include all of your routers in your analysis. For example, if you already have a fairly big core network, it might not be interesting to add thousands of ADSL aggregation devices or something like that to your simulation, because they all have exactly the same topology. They're homed into one or two core routers, and there really is no point in simulating failures for every single of these devices, because you know if one of their uplink fails, traffic goes to the other one, so there's no point in simulating that. But if you remove them from the topology, it looks like your traffic is being sourced on the core routers, which works well for the normal scenario where everything is up and running. But if one of the core routers goes down, traffic will actually disappear from your simulation. While in real life, traffic will shift from one core router to the other, because all those access devices will send the traffic to the remaining core router. To properly simulate this without having all these hundreds of thousands or whatever devices in there, you can actually just generate a virtual router. So if we have the picture here on the left with 3 access routers, you could replace that access router by one virtual router, which has the same topology because it has the same uplinks. You just add all the traffic you had from the 3 routers to that virtual router, and everything I've discussed before still applies in exactly the same way. If you have a different topology, like on the right, where you have a small ring with a chain of routers between the 2 core routers, you can do exactly the same thing, but here you will need 2 virtual routers, because you need to decide whether in the normal case traffic is going to the left or to the right, and putting the right metrics on those virtual routers, you can give exactly the same simulations. Again, I've seen several networks where this is being done simply because there's a whole regional network attached to the core or something like that, which at that point are not interested in simulating, but leaving it out might actually give problems if the core routers or some links to the core routers fail, because the real network would have shifted the traffic. Then a last note about multicast. I put it in here for the first time. In the previous tutorials I didn't have it, but we see much more deployment of especially IPTV-like services. So you have multicast traffic from 1, 2, or 3 sources in the network to a lot of POPs in the network or different locations, but as one very large stream or a whole group of streams having exactly the same destinations. A very common scenario is, for example, a cable network where they have a common feed which goes to all their regional cable headends, and they use multicast for distribution. Because this type of multicast traffic often has a very large volume compared to some video conference over the internet or something. This, in the examples I've seen, is traffic up to a gigabit per second, which if you run it over an OC48 backbone actually becomes a very significant amount of traffic to take into account. The good thing here is that measuring the traffic is much easier than it is for unicast traffic, because the flows are already there. The multicast group defines exactly where the traffic comes in and where it goes to. So there is nothing you need to aggregate there in moving or transforming source and destination IP addresses to ingress-egress. You already know what the flows are. On the unfortunate side, the interface counters on the router don't seem to give multicast bytes. So there are 2 MIPs which are relevant here, the IPM route MIP, which tells you exactly, I have these groups on these router, multicast groups, there's so much traffic on every of these groups. It also tells you where the traffic is coming into the router and where it's going out of the router. So Measuring multicast traffic is in this sense much easier than it is for unicast traffic, because this whole issue of generating the traffic matrix from flow records and etc. really doesn't exist here. You can even look at the PIM map, which gives you also an idea about the topology on where the multicast adjacencies exist. I don't have much more about this topic, but I thought it was relevant to bring it up here. There is a very nice project from GRNet. They have made a multicast weather map. There's a URL to the to the website where you can see how it works. And also somewhere on the GRNet website there is a very nice PDF with the whole explanation on what they implemented and how it worked. And there you can find much more details on how to measure the multicast traffic matrix. So a quick recap of what I've been talking about. So on the NetFlow side, it just takes a lot of resources to do the right thing. If you already have systems deployed like Arbor or AdLex for other purposes, it's a very good idea to actually extract the data from that for getting your traffic matrix, for doing resilience analysis or anything like that. If you really need to start the deployment just for that purpose, I think the BGP Next Hop aggregation is the one to have a look at, because it basically directly gives you the information you need with the least amount of overhead. BGP policy accounting and DCU are very simple to use and very effective, especially with the later Junos releases where you have 126 classes for DCU. I think you can cover most of your traffic using that method. For MPLS, people running a full mesh of traffic engineering tunnels already know that you get good statistics from them. People who don't run it are not going to run MPLS-TE just for that purpose. The LTP method is very simple, especially if you have a Juniper. You basically can get directly the traffic matrix from the CLI. On Cisco, you need to do a little bit more work and have a look at the paper from Deutsche Telekom to see how you actually should implement the algorithm. Then for the estimation, I think it's very useful, and I think more people should have a look at it and don't be too afraid of what it's exactly going to do. As I said at the beginning, I'm always interested to receive feedback. If you think something's incorrect or should be covered, sorry, let me know, and I will make sure to include it for the next tutorial, if that happens at any time. At the last page, the references to some of the papers I've been talking about. And that basically ends the tutorial. So, thank you for your attention.